positron emission tomography machine, so a PET scanner. Okay? Now this is going back to the fact that we know, so a PET scanner or a PET scanner, okay? If inside the brain you use an alpha emitter, not an alpha emitter, a positron emitter, okay? So the person, what they would do is they'd take this tracer, it would produce a positron inside wherever the tumor is. The positron would be created, okay? They would start moving. We know that positrons, if they meet electrons, which is very likely going to happen very quickly, the positron will not move very far before it meets the electron. When they meet, they annihilate, they destroy one another, okay? They disappear, and out from that destruction, you produce 2 gamma rays, okay? This is very similar to momentum. When you look at 2 things that collide, they have to be conserved. For example, if you hit a snooker ball at this one like that, they have to go like that so that the total momentum is conserved. If a positron and an electron meet like that, the gamma rays will be produced like that. If the positron and electron met like that, they'd be produced like that. So it keeps that symmetry. Now if you have scanners around the outside and you detect gamma here and gamma here, you can follow those 2 lines back and say, okay, I think the positron was annihilated here. That must be where the tumor is in the brain, okay? Because the tracer that you use will produce a positron, all right? It will undergo beta-positive decay, but we know that a positron will not travel far before it annihilates an electron, so I can say, with quite a lot of certainty, wherever I detect the 2 gamma, if I follow them back along a straight line, they probably were produced there, and that is where the tumor will be. Okay? So that's another thing. You've got a PET scanner, you have radioactive tracers. You can also obviously use gamma for killing cancer. Alright? You can use radiotherapy, you can use gamma from outside, and you can focus the beams of gamma to where the tumor is, and you fire it. We know that it will pass through most of the flesh, the tissue, the skin, because it has a large penetration depth. It will hit the tumor and it will have enough energy to actually kill the cancer cells, okay? Alternatively, you can obviously treat cancer from inside as well. Instead of using radiation therapy, you can actually make the patient swallow or take radioactive elements, and it will basically find the tumor and it will emit alpha or beta to be able to destroy the cancer from inside, okay? But you need to use alpha or beta because it will destroy the cancer straight away when it's produced. If you use gamma inside, it is going to leave the body. So the only time you would use gamma from inside is if you were using it to detect the cancer and detect it outside, yeah? You would not use gamma inside to kill it inside unless you're focusing it at the tumor. There is a risk, obviously, that the gamma or the other things can kill good, healthy cells, but obviously the risk is worth the reward, okay? Dangers of radioactivity. So this one's quite short. Your dangers are, we've discussed it over and over again, they're ionizing radiation. Either you can get radiation burns, which can lead to radiation sickness. If you have a look at the photos, most of the time it will burn the skin, it will look red. Most of the patients that you see are being treated, obviously they lose their hair and things like that, so it's killing healthy cells. That's if you are irradiated by it, which means you are exposed to the radiation. If you move away, so irradiation, you are in the vicinity, you are close to a radioactive sample, you are being irradiated by the ionizing radiation, okay? If you move away from it, you're fine. That's irradiation. If I move away from the sample, I'm no longer in proximity with the ionizing radiation, so I'm not exposed anymore. Contamination is when the radioactive material is either on your skin, on your clothes, or inside you. If I am contaminated and I put the sample and I swallow it, for example, and I walk around the school, it's going to be inside me, it's going to be emitting ionizing radiation constantly. I'm not walking away from it, yeah? Inevitably, that will obviously lead to mutations in cells. It will kill me depending on what it is over a specific amount of time. You have to be very careful if you use an internal tracer, okay? You swallow and you have radioactive material inside you for medical reasons. You need the half-life of the sample to be very short. If you take a sample that has a half-life of 1,000 years, then not until 1,000 years will it have halved its radioactivity. That's 1,000 years. Obviously, if you're using medical radioactive materials, they have to be hours or days. So that in 1 day, it's halved. 2 days, it's quartered. 3 days, and so on, and eventually maybe a week, gone. Yeah? If the half-life is too long, you are going to be contaminated for a lot of years. Okay, so you have to be very careful with which one you choose. Handling the radioactive materials, obviously you don't just pick them up with your hands. Use long objects. If it's alpha, putting that much air between you will stop the alpha. So use tongs, for example, to pick them up, move them around, move away from them. Do not give a patient treatment and stand next to the patient while they're being treated. Give the patient treatment and leave the room, okay? So do not irradiate yourself, move away. If you're contaminated, that's different. You have to remove the sample or wait for it to decay. All right? You can stop that one there.